Continuing further, what we are discussing is that the moment at end B for this simply supported beam would be such that it would cause, if to cause a unit slope at end B, that would be equal to 3EI by L. तो उसका ये मतलब है कि if we, as we obtained here, the moment required at B was 4EI by L. Now here it's 3I by L. Here the quantity 3EI, the value 3E, EI by L is the stiffness of this beam. This is the stiffness of this beam. So for a simply supported at both ends, the stiffness is 3EI by L, and for one where it's fixed at one end and simply supported at the other, it's the moment required at end B is 4EI by L. Thereby the stiffness is 4EI by L. You have to remember this. For fixed and simply supported, it is 4EI by L, and for both ends being simply supported, it's 3EI by L. Now, if there are many members, which are getting connected at a single point. Now, if this is fixed, for example, this is fixed, this is point A, or the joint or the support A, then we have another one, it's also fixed, it's B. Then we may have the third one, let it be hinged, and if this is hinged, this is C, let there be another one. Now this is D, it's again fixed. Now if individual members, these are all members or elements. Now this point at the center, if this is O or 0, it's O. Now this is, what is the property of AO? Let it be I1 is its moment of inertia, and the modulus of elasticity is same for all, it's E, and the length of this member is L1. For OB, it's I2, modulus of elasticity is E, and this is L2. For OC, it's I3, the modulus of elasticity is E, and its length is L3. This is I4, E is its modulus of elasticity, and L4 is the length of OD. Now, what do we get? We get OA is the similar thing. It's fixed. If I take OA, it's fixed at A. It's simply supported, although ridged, at O. Similar is the case with OB as well as OD. But in case of OC, it's simply supported at C and simply supported at O. So now you had the two cases. पहला case हमारे पास, that was OA fixed and simply supported at the other end O. Now this is the case number 1 that we discussed, wherein M was equal to 4EI by L for a unit slope. Thereby, if I know if I have to determine m1, now what is m1? M1 is the moment that is generated at end A of OA. M1 is the moment that is generated at end A, or it's given to the end A of OA when a unit, when a slope, or we can say a slope theta. Let me take theta from here. Theta, when a slope theta acts at end O of OA. Now, because O is ridged, O point O is ridged, so the slope at O will be maintained between all elements. Now all these elements are OA, OB, OC, OD. These are all elements. Between them the slope will be maintained. Thereby at O the slope will always be it will be theta. It will always be theta between all elements, between OA, OB, OC and OD. So as we were determining M1 here, M1 is now equal to, this is not end, and this is not end A, this is end O. This is end O. So M1 will now be equal to 4EI by L. Now E is same everywhere. It's I1 for first OA. It's I1 by L1 is the length into, then you have theta. So this is the first equation. Similarly, M2 is 4EI2 by L2 into again theta. Then you have M3, it's 4EI3 by L3 into, you have theta. Is it? It's not. For third case, it's 3AI. So for third case, it's M3 is 3EI by LI3 by L3 into theta. And for the fourth case, you have 4EI 4 by L4. तीसरे केस में चेंज क्यों हुआ? Because it was simply supported at both ends into theta. So now if I have a look at this, in every case you have a ratio on the right side, जैसे I1 by L1 है. Similarly you have I2 by L2, I3. Now if you have a look, I3, let's first take these ratios, I4 by L4. they're one sort of ratios. Now I3 by I4, I3 by L4, L3 is actually equal to 0.75 times, it's 3 by 4 times, it's actually 0.75 times what we are getting in above, I1 by L1 or I2 by L2 or I4 by L4. It's, so we can say that it's 3 by 4 times the other ratios. Thereby, if we take the ratio of all of these, now we have four equations. Above we saw four equations. M1 was equal to 4EI by L1 into theta, M2 4EI2 by L2 into theta, M3 3EI3 L3 by L3 into theta, and M4 4EI4 by L4 into theta. Thereby, now we have, if we take the ratio of M1 is to M2 is to M3 is to M4, if we take these ratios, what do we get? Because E is the model of elasticity and it's constant for all the elements, so it will go once we are taking the ratios. So ratios में ये चले जाएगा, this value. Then what will remain is I1 by L1 is to I2 by L2 is to I. Now this will be 3 by 4 times I3 by L3 is to, so this is 3 by 4 times I3 by L3, and then you have I4 by L4. So these are the ratios between the moments. Then M1 plus M2 plus M3 plus M4 would be equal to M. Now all these at point O, if they are all together equal to M, we have now four individual moments, M1 acting due to at this point, this is 1, then we have M2, then we have M3, then we have M4. So when we are adding them all, we are actually getting the overall moment M. So if they are all equal to M, then what do we have? Let us resolve this. M1 will be, you can take the ratio M1 by M then, and you can get the amount of stiffness that's distributed in member M1. Similarly, M2 by M, so you can get the amount of moment that's distributed in. Now how will this be distributed? This is all distributed in terms of stiffness factors. This is all getting distributed in terms of stiffness factors. Now what is a stiffness factor? It's very important to know what is a stiffness factor. A stiffness factor is, we can say, the values that we just got for I1 by L1, then I2 by L2, they were all stiffness factors. Like for example, you have L1, this was a stiffness factor for OA, then I2 by L2, this was a stiffness factor for OB. So every member now has a particular stiffness factor. So the moment will be distributed in terms of the stiffness factor. So it will be equal to, अगर हम total moment, what will, let me show you one of the examples here. For example, if I determine M1 by M, now What will be m1 by m? What is m1 equal to? It's 4e. Now, if we take it in the terms of ratio already, then it will be equal to I1 by L1, then into M, because it's MEI by L, now divided by E चला जाएगा between the top and the bottom, नीचे भी E आएगा, so I'll not write down E value, divided by what is total M? It will be I1 by L1 plus I2 by L2 plus I3 by L3 plus I4 by L4. Now, I3 by L3 had 0.75 because it was 3 by 4 times. So, now this, what do we get here? अगर मैं यहाँ से निकाल दूँ this much portion, this much portion, this much portion, it's coming out to be a separate ratio. Now, what is that ratio? We can call that as R1 for this member, and it will be equal to into M. So the ratio R1 is I1 by L1 divided by I1 by L1 plus I2 by L2 plus so on. So R1, what is R1 now? What do we mean by R1? R1 is the moment distribution factor. R1 is moment distribution factor. Similarly, for second OB element, R2 will be the moment distribution factor. Then you will have R3, the moment distribution factor, and similarly R4, the moment distribution factor for OD. So every member will have its own moment distribution factor. But what do we mean by now? What do we mean by moment distribution factor? R, its stiffness of one member, because it's I1 by L1, its stiffness of one member divided by its stiffness of all members. So the moment distribution factor is the stiffness of one member to the stiffness of all the members that are acting at that joint. तो एक जॉइंट पे अगर 4 मेंबर एक्ट कर रहे हैं तो किसी एक मेंबर में मोमेंट डिस्ट्रीब्यूशन फैक्टर वुड बी द स्टिफनेस ऑफ वन मेंबर ऑफ दैट मेंबर विद रिस्पेक्ट टू द स्टिफनेस ऑफ ऑल मेंबर्स. तो यहां से हमें निकलता क्या है? व्हाट डू वी गेट? वी आर एक्चुअली गेटिंग, if we know the total moment that's acting at one particular joint, we can then distribute that moment into different elements. तो यही है moment distribution method. If we know the total moment m at a particular joint, we can distribute that moment separately into different members. Now, how is it distributed? It's distributed, which I told you first, it's distributed in terms of, I told you this, it's distributed in terms of the relative stiffness. So we know here if we know here the relative stiffness of every at a particular joint for every member or an element, we can then determine the distribution of moments within each of the elements. Now, I'll just take one question and you will get an overview of what we are actually doing. For example, this is a beam, it's fixed here, and it has got a simple support at the other end. This is end A and this is end B. The total length of this beam is L. If this total length is L, for example, you have a continuous uniformly distributed load acting on this beam, a UDL load which is acting on this beam, and the UDL load that's acting is W, small w, per unit run is the load that's acting here. Now this end is end A and this is end B. Now in moment distribution method, what do we do? How do we solve this question? What we do is that in the first step, this is the first step. In the first step, what we do is that हम दोनों ends को clamp करते हैं. What we are actually doing is that we are actually fixing both ends, although end B is not fixed. So ये भी fix हो जाएगा and this is also fixed. The two ends are now fixed. Then in second step, what we do is that वही इसी पे जो हमने अभी बनाया, what we do is that we apply loads, the load that's given here. We apply this load on. Now what will be the fixed end moment? So we then calculate the fixed end moments. In slope deflection method, you must have and you should have solved this when both ends were fixed and the load that was acting is W per unit run. What do we get? We get minus W L square by 12 at one end. Now this is clockwise. The movement is clockwise here. Roll number 41, you are writing on the screen. Then you have at the right end WL square, it will be plus. Now this is also clockwise here at this end, that's the convention. This will be the fixed end moments. You have already solved this from the slope deflection method. That's where from we are taking the values. Now, but what was the actual question? Any of you, the actual question was, it was fixed at A and simply supported at B. But what we did is that we fixed it at both ends and applied the load. And then we determined the fixed end moment for the load W per unit run. We took the same load W per unit run and applied it here. And then we got the fixed end moment at A minus WL square by 12 clockwise and plus WL square by 12 clockwise at end B. Then in the third step, we are coming to the actual question. What do we do? Now we release the moment at end B. Now how do we release? What should be the actual moment, fixed end moment at end B? Any of you? What should be the actual fixed end moment if it's simply supported? If not fixed, कितना moment होगा simply supported पे? Any of you? There are 59 participants. Any of you can answer Not one of you is answering. If the end B is simply supported, what's the moment? How much is the moment at end B if it's simply supported? It's zero. Roll number 77. It's zero. It should be zero. So what do? We minus WL square by 12 at this end, and this will be an anti-clockwise प्लस डब्ल्यू एल स्क्वायर बाई 12 को मैंने माइनस डब्ल्यू एल स्क्वायर बाई 12 कर दिया such as to make the overall moment to be zero because at simple support the moments are zero. But for that, what do we need to do? We need to give an anti-clockwise moment minus WL square by 12. This is anti-clockwise moment that we are applying at end B. It's equal to minus WL square by 12. So it was same like applying moment M at end B. And that will lead to fixed end पे कितना moment जाएगा? How much will be the moment at the fixed end now that will be transferred? Let me recollect. This was the question. If we applied moment M at B, the amount of moment that was transferred was M dash was equal to M by 2. तो आधा moment यहाँ जाएगा. Now this is known as carry over. The amount of moment that's transferred once we apply the moment WL square by 12 here, it will be half times at end B. It will be minus WL square by 24, and the direction would be same anti-clockwise. So now we have it's also anti-clockwise. The direction is like this. It's anti-clockwise. So in the third step, what we have actually done is that we have given the moment at B and minus WL square by 12, and the moment was carried over. This is known as carryover. The moment was carried over here to this end. Half of the moment was carried over. This is known as carryover moment. It's known as carryover moment. So now what is the total moment at both ends? मैं इसको सीधे एडिशन कर लेता हूँ. This is the method that you use in moment distribution method. First of all, let me cancel this. This is not 0. This overall is 0. Plus WL square by 12 minus WL square by 12 is overall equal to 0. Now at this end, it's minus WL square by 12 minus WL square by 24. So the total moment is, what will be the total moment? Minus WL square by 12 minus WL square by 20. So it will be 3 by
minus WL square by 12.
It will be minus 3 times WL square by 8. Sorry, 24.
24.
24. So it's minus WL square by 8. It's minus WL square by 8. So the amount of moment that's transferred here is WL square by 8. So we have now got the amount of moment at M and A, the total moment at and A, it's minus WL square by 8. At end B, it's 0. At end B, MB is equal to 0. This is simply supported. So if you want to draw the moment diagram, the moment diagram of this question would be like this. It would be somewhat like this. Not like this. So this is the type of bending moment diagram that you get here. This is end A, this is end B, this is positive sagging here, positive value here for sagging happening. Here it will be negative value. It will be for hogging. Here we got the negative value minus WL square by 8. We got the value 0 here. Now can you determine this value?
WL square by 16.
Here, this one. It's WL square by 16. So you can solve this determining the value here at say any other point MC. How do you do with this? You have to determine the moment which is maximum. The maximum moment you have to determine. And you must have done this in slope deflection method. And you will try this. You will get WL square by 16. Is it? I have not tried this, but probably it's WL square by 16. So you can also get another point from this end. First of all, you will get this distance x at which the counterflexure is happening, and the moment here is moment at this point, say this is D point, is 0. So you can get the distance x at which moment is 0. So once you got the moments, you can then go for shear forces. In this lecture, we would